We'd like to find the area between the graph of y equals x squared and the x-axis from x equals 0 to x equals 5. And we'd like to do a little bit better than just approximating. Let's see how this is done. Let's start by dividing up the interval from 0 to 5 into n subintervals. So let me rewrite the x-axis here. And we have 0, 5. We're going to create n subintervals. So if we're dividing up the interval from 0 to 5 into n subintervals, each one has a width of 5 over n. 5 over n is the width of each one. So our first subinterval here is at 5 over n. The second one is at 5 over n times 2. Then we have 5 over n times 3, 5 over n times 4, 5 over n times 5, 5 over n times, let's call it I, all the way up to the very last one, which is 5 over n times 5 times n. I've redrawn our function y equals x squared, and we're going to create a rectangle above each little subinterval, where the height of the rectangle is determined by the right endpoint of the subinterval. So we are going to create an AreaUsingRRAM with n subintervals, a right rectangular approximation with n subintervals. So graphically it looks like this. The rightmost rectangle has its height determined by the x-coordinate of 5, which remember we called 5 over n times n. The next rectangle has its height determined by the x-coordinate just before that. And just to give you a few more arbitrary looking rectangles, we go up along the right endpoint and we make a rectangle, and here is one right in the middle. So let's call this point 5 over n times I. And we want to find the area. The area of this entire region can be approximated. So far we're still doing an approximation. Can be approximated by finding the area of each rectangle and adding them up. So the area of each rectangle is, as I'm sure you remember from geometry, it's the width times the height. And let's focus on this rectangle right here. So the one that I've highlighted in pink. The area of that rectangle, the width, well, the width of every rectangle is 5 over n. And the height of that rectangle is the y-coordinate corresponding to this x-coordinate. So the y-coordinate corresponding to that x-coordinate is 5I over n squared. Or we get 5 over n times 25I squared over n squared. Or, simplifying that just a little bit more, that's equal to 125I squared over n cubed. That's the area of each rectangle. Let's take that and add up all n rectangles. So we have 125I squared over n cubed. 125I squared over n cubed. And we want to add that all up for all the rectangles I going from 1 to n. So notice that the 125 and the n cubed have nothing to do with the index of summation, so we can pull those out in front of the capital epsilon. the capital sigma, 125 over n cubed, and we're left with sigma, the sum, I goes from 1 to n, of I squared. And this expression right here is probably somewhat familiar to you. You may not remember exactly what that sum is equal to, but you probably remember from your pre-calc class that that is one of the special sums, and that adds up to n times n plus 1 times 2n plus 1 over 6. For now, we're just going to have to, well, you'll just have to trust me on this one. But if you want to look into proving it, you can prove that using proof by induction. That's a topic for another lesson. For now, you're going to trust me on that. So now our area is equal to, I'm purposefully leaving a little bit of space here, 125 over n cubed times n plus 1 times 2n plus 1 over 6. That's not really our area. That's our area when we have n rectangles. But we really want to have more and more and more and more and more rectangles. So we're going to take the limit as n goes to infinity. And now this works out quite nicely because the limit as n goes to infinity. Let's pull out the 125 over 6, separate that from the n times n plus 1 times 2n plus 1 over n cubed. So I want the limit as n goes to infinity of the 125 over 6 can be pulled out, and this part is a rational function. I have a cubic on the top and a cubic on the bottom, and the limit as n goes to infinity. If the degree on the top is the same as the degree on the bottom, it's just the ratio of the leading coefficients. And if you look at the leading coefficients here, if you would, not that you have to, but if you would multiply out the numerator, your leading coefficient would be 2n cubed, and on the bottom you have just a plain old n cubed. So the ratio of the leading coefficients is 2 to 1. And so our final area is 125 over 3. And that's our final answer. It wasn't so hard, but what we'll see is that it's even easier once we learn the fundamental theorem of calculus.